December 8, 2020. A brand new Boeing 777X suddenly pitched violently up and down during a test flight. No pilot input, no warning. Boeing's test pilots fought for control while engineers watched in horror. Their flagship comeback aircraft, the one that was supposed to prove Boeing could still build planes after the 737 MAX disasters, was experiencing the exact kind of uncommanded control problem that had claimed the lives of 346 people. But it wasn't always like that. You see, when Boeing launched the original 777 in 1990, the company was operating at the peak of its engineering prowess. It took Boeing just 4 years from program launch to first flight, and the 777 entered commercial service barely a year later. By any measure, it was a masterclass in aerospace development. A clean sheet design executed with precision, delivered on schedule, and built to dominate. But everything changed in 2011 when Airbus upgraded their A350-1000, strategically positioning it as a modern alternative to the 777-300ER, aiming straight at Boeing's most profitable segment. For Boeing, the threat was clear. They needed a response, and quickly. So in 2013, just years after this development, Boeing launched the 777X, a highly efficient, massive jet that would make the A350 program obsolete with an entry into service planned for 2020. The plan was straightforward. Use the proven 777 fuselage, add new engines and wings, and dominate the market before Airbus could gain traction. Boeing's engineers were confident. After all, they were simply upgrading an already successful design with new engines and wings. What could possibly go wrong? Today, more than 13 years later, the 777X still hasn't entered service. Development time has stretched to nearly triple what the original 777 required, and the delays keep mounting. In fact, in January of this year, Boeing discovered yet another problem that could push deliveries into 2028. The program that was supposed to save Boeing's dominance has become an engineering disaster. So what went catastrophically wrong? How did the 777X go from sure bet to one of the most troubled aircraft programs in modern aviation history? To understand how Boeing's 777X turned into one of aviation's most troubled programs, we must first appreciate the brilliance of what came before it. You see, the late 1980s presented Boeing with an obvious gap in their product lineup. The Boeing 767 could cross the North Atlantic and connect major hubs with smaller cities, but it lacked the range for truly long-haul routes. On the other hand, the mighty 747 could fly anywhere in the world while transporting massive numbers of passengers, but only a few airlines could justify its economics. So airlines wanted something in between, an aircraft with the 747's range, but sized for routes with somewhat less demand. Previously, Boeing had attempted to serve this market with the shortened version of its iconic jumbo jet called the 747 SP. While this aircraft made sense for certain distant city pairs, its 4-engine configuration meant its economics could never be compelling enough to achieve widespread adoption, selling only 50 units. For a brief period, Boeing even considered giving this new aircraft 3 engines and a layout similar to the McDonnell Douglas DC-10, but that concept was quickly abandoned. Instead, Boeing made a decision that was quite unusual for the time. It invited airline customers directly into the design process from the earliest conceptual stages to provide genuine design input, not market research or focus group feedback, but actual engineering specifications. In fact, it was Cathay Pacific's request that helped push Boeing to increase the fuselage diameter, resulting in a wider cabin, something that would later become a signature feature of the 777. This working together philosophy represented Boeing's collaborative culture at its peak, a stark contrast to the company's approach in more recent decades. Boeing took these requirements and committed to a clean sheet design that would incorporate numerous innovations, and the plane that emerged embodied Boeing's true engineering excellence. 777 became the first commercial aircraft designed entirely using computer-aided design, eliminating the need for physical mock-ups and dramatically reducing development time. It introduced fly-by-wire controls to Boeing's commercial lineup, replacing mechanical linkages with electronic systems that offered unprecedented precision and flexibility. Its enormous engines, the most powerful ever fitted to a commercial aircraft at the time, were marvels of engineering in their own right. Moreover, the 777 entered service with a 3-hour ETOPS rating, meaning regulators trusted its reliability enough to allow flights 3 hours from the nearest airport, a testament to both Boeing's engineering and the confidence it inspired. Perhaps most remarkably, from launching the program in 1990 to the delivery of the first production 777-200 in May 1995, Boeing took just over 5 years to achieve this feat, an absolutely unthinkable time frame by today's standards. Over the following years, the 777 quickly became the new standard for long-haul operations, and Boeing wasted no time expanding the concept into a complete aircraft family with longer fuselages, more powerful engines, and refined aerodynamics. The definitive variant became the 777-300ER, capable of carrying between 350 and 400 passengers depending on configuration, while maintaining the range to connect virtually any 2 cities on Earth. The 300ER became so capable that some airlines began using it to replace their Boeing 747s on routes where passenger demand didn't justify the jumbo jet's full capacity, making it one of the most commercially successful wide-body aircraft ever built. However, this competitive landscape began to shift dramatically when Airbus launched its A350 program in 2006. Airbus initially wanted to design the A350 as a relatively straightforward update to their aging A330, fitting new engines and a redesigned wing to an existing fuselage. But the A330's basic design dated back to the A300, which had entered service in the 1970s, meaning the fuselage had already been updated once for the A330. And market sentiments revealed that airlines wanted something genuinely new, forcing Airbus to develop an entirely clean sheet design featuring advanced composite construction and cutting-edge systems. While the smaller A350-900 didn't really affect Boeing's 777 sales, the larger A350-1000 posed a direct threat to Boeing's dominance in the long-range wide-body market. Airbus had strategically positioned it as a modern alternative to the 777-300ER, promising better fuel efficiency, lower maintenance costs, and the operational flexibility that came with a newer design. For Boeing, the threat was clear. They needed a response, and quickly. But there was a problem. You see, the early 2010s was a period when Boeing was going through a lot of chaos across multiple programs. The 737 MAX had just been announced in response to Airbus's A320neo launch. The 787 Dreamliner, which had finally entered service after years of delays, was now experiencing highly publicized problems, including lithium battery fires that would eventually ground the entire fleet. And Boeing was also working on the newer stretched version of the 787, the 10, which strained its engineering resources even further. So rather than develop an entirely new aircraft, a process that would take years and cost billions, Boeing chose to upgrade the existing 777 with new engines and redesigned wings. In fact, they had no choice. Airbus was planning to deliver the A350-1000 by 2017, and any significant delay in launching a competitive Boeing product would have meant handing Airbus years of unopposed market access. So Boeing immediately pushed forward, officially launching the 777X program in September 2013, with Lufthansa and Emirates as the launch customers. The 777X may have been based on the existing 777, but Boeing left no stone unturned to make it future-proof. The 777X's most distinctive feature was its folding wingtips. These folding wingtips weren't merely an engineering curiosity, they were essential to the 777X's commercial viability. Without them, the aircraft's massive wingspan could have pushed it into a larger gate category, limiting airport access and dramatically increasing handling costs for airlines. The engineering challenge was substantial.
The folding mechanism needed to be lightweight, reliable, and capable of withstanding the aerodynamic loads experienced during flight. So Boeing constructed an entirely new composite wing manufacturing facility in Everett, Washington to build these revolutionary structures. Powering the 777X were General Electric GE9X engines, massive turbofans evolved from the GE90 that already powered the 777-300ER. These engines were so large that the cowling diameter exceeded the fuselage width of a 737, with each producing roughly 110,000 pounds of thrust, making them the most powerful commercial turbofans ever built. Boeing assumed this conservative approach to redesign would accelerate development, with entry into service planned for 2020. After all, they'd already developed composite wing technology for the 787 and the fuselage design was proven. But what Boeing didn't fully anticipate was just how many seemingly minor changes would compound into major obstacles. The first cracks in Boeing's optimistic schedule appeared early. While the 777X would use an aluminum fuselage similar to the original 777, Boeing decided to construct key sections of the airframe with aluminum lithium alloy, a newer, lighter material already used in aircraft like the A350. While this change alone would add complexity to the development timeline, Boeing hoped that the weight savings justified the risk. To offset that, Boeing introduced a revolutionary plan that would transform how the fuselage was assembled. You see, traditional aircraft manufacturing is extremely labor-intensive. Each airliner requires millions of fasteners called rivets to join fuselage sections together, and for decades, much of this work was done by hand, one fastener at a time. Boeing decided to revolutionize this process with a system called FAUB, Fuselage Automated Upright Build, where robots would automate the riveting process, theoretically saving enormous amounts of time and money while improving consistency. But it turned out that the FAUB project didn't meet its bold expectations. Since its inception in 2015, the problems emerged almost immediately. Rather than speeding up production, these automated systems created defects that Boeing's workers, the very people the system was designed to replace, now had to fix manually. Boeing initially dismissed these as teething problems, hoping that the system would improve with refinement and experience. But as months turned to years, the fundamental issues persisted. In late 2019, Boeing made a humiliating announcement. They were abandoning the FAUB concept entirely. Some automation was eventually introduced for specific tasks, but the grand vision of robot-assembled fuselages had failed, wasting years of development time and substantial investment. While the fuselage automation struggled, Boeing faced even greater challenges with the aircraft's wing. The 777X wing represented one of the most significant departures from the original 777 design. While the design itself was heavily borrowed from the 787, there was one critical difference: its manufacturing location. The 787's composite wings were built by Mitsubishi Heavy Industries in Japan as part of a risk-sharing partnership and shipped to Boeing's facilities for the final assembly. However, considering the size of the 777X wings, Boeing decided to build them domestically, constructing a brand new composite wing facility in Everett, Washington. This wasn't a small undertaking. The facility cost Boeing over $1 billion to construct, a massive investment even by Boeing standards. But Boeing deliberately built the factory with significant spare capacity, planning to use it for future aircraft programs, particularly the proposed new mid-market airplane, or NMA, which was later abandoned after the MAX crisis. Moreover, Boeing and its workforce faced a steep learning curve getting this enormous facility operational, and composite manufacturing at this large scale presented challenges that couldn't be fully anticipated in advance. By the spring of 2019, the program was behind schedule by at least a year, and there were concerns that these issues might worsen, cascading into even longer delays. But those concerns would soon become secondary. On March 10, 2019, Ethiopian Airlines Flight 302 crashed near Ajera, Ethiopia, just 6 minutes after takeoff from Addis Ababa, claiming the lives of all 157 people on board. This was the second deadly crash involving the brand new 737 MAX in just 5 months. What followed was the worldwide grounding of the MAX fleet while Boeing faced criminal investigations, congressional hearings, and a complete collapse of trust with aviation regulators globally. The company would ultimately pay over $20 billion in compensation, penalties, and lost revenue. But the MAX crashes didn't just destroy Boeing's reputation and finances, they also raised serious questions about the FAA's credibility. You see, until the MAX crashes, the FAA had delegated substantial certification authority to Boeing's own employees. Boeing personnel authorized by the FAA would conduct much of the testing and validation work themselves, allowing them to move quickly through the certification process. This system was built on the trust that Boeing's engineers would verify compliance with safety regulations, but instead, Boeing abused this system to accelerate the certification process. Following the MAX crashes, the FAA announced sweeping changes. They would now conduct far more certification work directly rather than delegating to Boeing's own employees. This meant FAA employees now needed to be physically present at Boeing facilities, watching tests, reviewing data, and validating processes. And what followed would prove exactly why this direct oversight mattered. In September 2019, a 777X fuselage catastrophically ruptured while undergoing pressurization tests with simulated high-G loads. The pictures of this quickly went viral, and media coverage immediately suggested that Boeing had a fundamental design problem that would require months or years to resolve. While this was bad news for Boeing's already tarnished reputation, the reality was more nuanced. The failure occurred during ultimate load testing at 148% of limit load, just 2% short of the 150% required for testing. While concerning, this represented a marginal structural issue rather than a fundamental design flaw that could be addressed with reinforcements. But what happened next would derail the entire program, delaying it by years. On December 8, 2020, a Boeing 777-9 test aircraft experienced a serious uncommanded pitch event during a test flight, where the nose of the plane pitched up and down abruptly without pilot input. This event, occurring just as Boeing was attempting to regain its footing after the MAX accidents, sent shockwaves through the flight test program and immediately caught the attention of a now hyper-vigilant FAA. The reaction from the FAA was swift and unusually public. In a pointed June 2021 letter, the agency told Boeing that the 777X was simply not yet ready for type inspection authorization, a critical milestone that allows FAA pilots to begin their certification flight testing. The agency cited the pitch event as a primary concern, stating that Boeing had failed to provide a complete technical explanation for the incident or demonstrate how their fixes would work. Even more damaging, other regulators worldwide, particularly EASA, abandoned their traditional practice of rubber stamping FAA certifications and launched their own independent evaluations. The situation worsened further when Boeing made a strategic decision that would cost the 777X program dearly. With the 737 MAX 7 and MAX 10 still facing their own certification challenges, Boeing's leadership redirected engineering resources away from the 777X to focus on resolving the MAX issues. The 777X program effectively stalled as engineers shifted priorities, losing critical momentum and months of development progress. For an aircraft program already years past its original 2020 entry into service date, this resource diversion pushed certification timelines even further into the future, with no clear end in sight. Finally, in July 2024, 4 years and 5 months after the first test flight, the FAA granted type inspection authorization for the 777-9. This meant FAA pilots would now begin their own certification flight testing, and if everything proceeded smoothly, Boeing could start deliveries within months, a desperately needed relief for airlines like Emirates, Lufthansa, and Qatar Airways who had bet their future on this aircraft. Throughout July and early August 2024, everything appeared to go well. The test aircraft flew multiple sorties daily, methodically working through the FAA's checklist, verifying that all new innovations and systems performed as intended. Then, on August 15, 2024, one of the test flights landed at Kona International Airport in Hawaii after 5.5 hours of testing. The aircraft, which was supposed to be delivered to Lufthansa, completed its landing and taxied to the ramp without incident. But when Boeing's ground crew began their post-flight inspection, they discovered something that would immediately halt the entire program again. One of the engine's thrust links had failed. To understand why this discovery proved so catastrophic, we need to examine what thrust links actually do. These titanium components form part of the structure connecting each engine to the aircraft's wing pylon. Their purpose is deceptively simple. Transfer the enormous thrust forces generated by the engine to the pylon and through it to the rest of the airframe. But the engineering reality is vastly more complex. Consider the forces involved. Each GE9X engine produces almost 110,000 pounds of thrust at maximum power during takeoff, pulling the aircraft forward. During normal operations, these thrust links carry this load smoothly. But operating conditions on an aircraft are never purely normal. If one engine fails or throttles to idle during takeoff, that engine becomes a massive source of drag, effectively reversing the load on its thrust links. Or even worse, if a bird strike causes a compressor stall, the engine can oscillate between full power and zero thrust multiple times per second while vibrating violently in all directions. In this case, the GE9X featured 2 thrust links per engine, mounted at different angles so that either can independently carry the full thrust load if the other fails. This redundancy proved crucial in Hawaii. When one thrust link failed, the second maintained the engine's attachment to the aircraft. Boeing immediately grounded all 777-9 test aircraft for comprehensive inspections, and what they found shook the entire aviation industry. Additional cracks in thrust links across the entire fleet. While the exact number remains undisclosed, the pattern was clear. This wasn't an isolated manufacturing defect or a single flawed component. The problem was systemic, and more critically, even though General Electric manufactures the engines, Boeing designed the thrust link structure, meaning this failure falls squarely on Boeing's engineering. Boeing eventually resolved the thrust link issue through redesigned components and a better inspection approach. But in late January 2026, Boeing and General Electric discovered a new durability issue affecting the GE9X engine during routine inspections. Boeing has yet to disclose the full extent of the problem, but it is said that they are working with General Electric to resolve it. The 777-9, which was initially meant to enter service in 2020, continues to struggle, and while the first delivery has now been pushed back to mid-2027, even that date remains uncertain. For Boeing, the 777X represents the ultimate irony. Where the original 777 took just 5 years from launch to delivery through engineering brilliance and collaborative culture, the 777X has already consumed 13 years and billions of dollars with no end in sight. The program hasn't just destroyed shareholder value and airline confidence, it's demonstrated that Boeing has completely lost the engineering excellence that made the original 777 possible. What was meant to be a straightforward upgrade has instead become a monument to Boeing's decline. Proof that the company that once redefined aviation excellence can no longer even upgrade its own masterpiece.